Okay. And now let's see if this works. Okay. No. All right, as soon as my, yeah, there we are. Okay, there we go. All right. So you can see everything, right? Yep. Okay.
Yes, the slides, you can see your slides.
And is it, so it usually goes for an hour with questions, or like how long should I speak for? I can
It's
moderate.
naturally 1 hour, and then maybe 5 to 10 minutes for discussion. And naturally, we like to
Okay.
take questions in between. If you want, then we can just insist the audience for that. Otherwise, at the end. So.
Okay, it doesn't matter. I'm happy to take questions whenever. I'll I'll get to it. I'll try to monitor the chat. I'm usually pretty good at monitoring the chat.
Oh, that's great.
So how is it going, Sujata?
Yeah,
it's going on.
Very busy.
Yes.
So, Eric, how are you?
I'm good. I'm good. You know, I'm in my house right now. You know, I've been lecturing at home the whole time, so I much prefer to be in the classroom at a blackboard. But you know,
Yeah, we are all doing the same thing, kind of the same boat.
yeah. And my daughter is upstairs. My daughter will. So my daughter's in seventh grade.
How old is she now? How old is she?
She's 12. She's 12.
Wow.
She's gonna turn 13 and in about a month. So
teenager.
yeah, so she's a teenager.
I guess I saw a picture in Facebook. She just turned recently, right?
Well, her birthday's in a month. In 1 month, she turns 13. So I'll have a full teenager in a month. So she already acts like a teenager.
So please give my regards to Lauren.
I will. Yes, yes, yes.
Eric, actually, we may take some 2 or 3 minutes more because people are joining right now. So.
Of course, take your time. Yeah, that's fine.
So, Eric, let me apologize in advance. I may have to rush off towards the end of your talk. As I
okay.
Yeah. Something related.
Okay, no problem. I won't say anything interesting at the end of my talk. Then I'll make it all really, really boring.
Thank you.
I have Zoom meetings all day long today, so pretty much straight through until this evening.
For us, you had to start from that early morning.
That's okay. I'm an early riser. I don't mind.
Oh, that's good.
Yeah, we will always see Eric with a coffee at hand early in the morning during all those conferences or LHC based.
So I guess that we can start. Okay. So
Okay.
yeah, I'm just in. So it's my great pleasure to introduce Professor Eric Paquet. He is an associate professor in the Department of Philosophy at the University of Maryland. Prior to coming to Maryland, he did his graduate work at the City University of New York, and he did his postdoctoral research at ILLC and as well as at Stanford University. His primary research interests are in logic, especially modal logic, game theory, social choice theory, and formal and social epistemology. His research has been funded by NWO, that is Natural Science Foundation, and a VD grant from the Dutch Science Foundation. Today, he is going to give a talk on using SAT solvers to find impossibility theorems about variable candidate axioms in voting theory. As always, I used to insist you, so I now also insist you to ask questions whenever you need it. And it's over to you, Eric.
All right. Thank you very much, and thanks very much for inviting me. So this is joint work with Wes Holliday from Berkeley and Sam Zahidin, who is actually an undergraduate student at Berkeley. So, the talk is going to cover. So we have a current paper, extending SAT solving approach to impossibility theorems in social choice theory. So that will be the main focus of the talk, but it's also going to draw on two recent papers that Wes and I have, where we sort of are thinking about a new voting method, which we call split cycle. Now, this talk, I'm not really going to say much about this new voting method that I'm interested in. I'm just going to talk about one nice property that this voting method has. All right, so the way the talk's going to be organized, I'm going to start by talking about an issue in voting theory, and then talk about, an impossibility theorem that two axioms cannot be jointly satisfied by any voting method, and then talk about how you use a SAT solver to find that result. So let me start with an example. Okay, this is like a very concrete example. It was actually based on an actual election that took place in Vermont. And we're going to start with the idea of a spoiler. So look at this election on the left here. There are just two candidates in this election, candidate D and candidate P. Okay, now the numbers up here, this means 37 people rank D above P, 29 people rank D above P, and 34 people rank P above D. Every reasonable voting method, any way of determining who the winner is, we're all going to agree that candidate D ought to be the winner, right? So D is the majority winner. So D is going to win that election. But now imagine a new candidate enters the race. Okay, so here we have one election scenario, and now we have this new candidate R that comes into the race. Now, candidate R doesn't actually do very well in the rankings. Candidate R is ranked last by these groups of people. So the 29 plus 34 people rank R actually in last place. And it's still this 37 people rank R in first place. Okay. Now, there are some voting methods that in this context would end up electing candidate P. Okay, now why does candidate P actually get elected here? The method that I actually used here is what's known as ranked choice. So ranked choice says if no candidate gets a majority of first place votes, then you're going to throw out the candidate that has the least number of first place votes. So we're going to throw out candidate D because D has the fewest number of first place votes. And if we get rid of candidate D in everybody's ranking, we see that candidate P ends up with a majority of first place votes. So according to that voting method, candidate P is the winner. Now, we think that this is bad. Now, why is that bad? Well, look what happened. Candidate D won in this election right here, when there's just two candidates, D and P. A new candidate comes into the election. A majority of people prefer the old winner, candidate D, to this new candidate. And yet the presence of this new candidate caused candidate D to be knocked out of the winning set. So we say that candidate R has spoiled the election for candidate D. Okay. So what we want to impose is a property known as stability for winners. So this is going to be an axiom of a voting method. And it says that if a candidate A will be a winner when an election is run with a set of voters X, not including B, and A would beat B in a head-to-head majority vote, then A is still a winner when B is included in the election along with all those in X. Okay, so your winning set needs to be stable in a particular way. Okay, so this is going to be the central axiom of a voting method that we're interested in. Just to illustrate this with a nice picture, with the type of diagrams we're going to be working with, rather than thinking of profiles as describing what everybody's rankings are, you can think of a profile as a weighted directed graph. And this edge right here, for example, means that the margin of victory for B over D is 3. That means 3 more people rank B over D than D over B. Okay, so what you can see with these two pictures right here, so first of all, we have this graph right here can be embedded in this bigger graph right there, right? So this graph just kind of shows up right there. We added this new candidate A, and there's arrows from B to A and also from C to A, but that doesn't actually matter. So the margin of B over A in this profile right here is 1. B is now minimax is just another voting method. B is a minimax winner in this little 3 candidate profile. In fact, every reasonable voting method out there, any voting method satisfying 2 fairness principles known as anonymity and neutrality, have to elect all candidates when your profiles give you this margin graph right here. So candidate B is a winner over here. Candidate A enters the election. A majority of people prefer B over A, and yet when with A in the election, B gets knocked out of the winning set. Okay, so stability for winners is not going to say that A can't win the election. So it might be that A enters the winning set. That's fine. What stability for winners says is that at the very least, because B's majority preferred to A and C's majority preferred to A, that B and C have to stay in the winning set. They can't get knocked out of the winning set with the presence of A. Okay, and minimax is an example of a voting method that fails stability for winners, and this example shows that. Okay. Okay, how is this relevant to independence of irrelevant alternatives? Very, very good question. So independence of irrelevant alternatives will rule out stability for winners. But as we know from Arrow's theorem and lots of that you in general, most voting methods do not satisfy an analog of independence of irrelevant alternatives. Now, Wes and I have identified a weakening of independence of irrelevant alternatives called coherent IIA that implies stability for winners. And our voting method, and one voting method, the one we like, does actually satisfy this weaker version of IIA. Okay, good. So there are some methods that do satisfy stability for winners. This method I'm not talking about, split cycle, then these other methods, getcha, uncovered set, and the trivial method. So here's one way to satisfy stability for winners. Don't make any distinctions. Just always elect everybody. In every election, always elect everybody. Then you will never violate stability for winners. So that's the trivial method that always elects all candidates. That satisfies stability for winners. Now, of course, we don't want a method that isn't discriminating. That's like you're not really, voting's not doing what it ought to do. Right. So, we want to rule out stability, the trivial method, because it elects too many people. It too often just says there's ties. And then when there's a tie, you have to hand it over to an even chance tie-breaking mechanism or something like that. There are some methods that do not satisfy stability for winners. Board account, beat path, minimax, rank pairs, plurality. So lots of methods do not satisfy stability for winners. So one natural question is, what's the difference besides what that they satisfy stability for winners? What properties do these voting methods have that these voting methods do not? Okay. Now, one of the properties we're going to focus on is how often a voting method is what I'll say irresolute. So a voting method is irresolute if there's a profile where it might select more than one candidate as a winner. That is, it identifies two or more people as tied for the win. Okay. In such a case, then when there's a win, you have to go to like a runoff election, or you have to do some type of tie-breaking mechanism. Okay. Now, there's a general theorem that says if you satisfy anonymity, all voters are treated equally, and neutrality, then every any voting method that satisfies those two properties must be irresolute. So there must be profiles where you might elect more than one candidate. But more generally, you could ask, this is kind of a quantitative question, how often do different voting methods elect more than one candidate, identify more than one winner? So here, I'm just going to flash some graphs in front of you. And these are simulations that I run, where you have 3 candidates and then a population of either 1,000 or 1,001 voters. So I kind of split that evenly to not have an even number of voters create more ties or anything like that. And what you're seeing here is essentially like what's called a Boxen plot about that specifies the proportion of profiles, randomly sampled profiles, or randomly election scenarios where you have 1, 2, or 3 winners. And you can see, since you have lines here, with 3 candidates, most voting methods elect a single candidate. As the number of voters increase, you can start to see certain distinctions, like this Condorcet method and these methods right here, more often than not are starting to select multiple winners, multiple candidates as winners. And when you go up to 5 candidates, you can see now uncovered set and split cycle, they're selecting multiple winners. Here we have Condorcet. These 2 methods are starting to select more. When we go up to 6, it's becoming even more pronounced. Now we have 10 candidates. And now we have something really cool happens. Let's jump up to 30 candidates. So this is really a huge election. What you see here, look at what's happening with getcha. Now we have this little blob down here, which basically means more often than not, getcha is actually electing 28 to 30 candidates. So actually just electing everybody. So getcha's starting to behave a lot like the trivial method. Okay. And in fact, we can run simulations where you essentially simulate an infinite number of voters. Now, obviously, we can't really reason about an infinite number of voters. What you have in mind is elections with a very, very large number of voters. And what you can see there is, if you take a look at uncovered set and getcha with like 30 candidates right here, you can see that the average size of the winning set is actually quite large. It's like 20, 22 out of 30, Okay. The other thing I want you to point out is split cycle. That number is not 1. It's, a little bit over 1. So this is showing that even sort of in the limit as the number of voters approach infinity, split cycle is identifying as winners more than one candidate. So the average is roughly around 2, but so it's not quite, so split cycle and Copeland have that property. Okay. So you might, well, we can skip that graph. You might think of another axiom that you would want your voting method to satisfy, which you might call asymptotic resolvability. And what this says is, as the size of the voters, as you get more and more voters, the probability that there's a tie in the margin of victory for 2 candidates, that's going to go down to 0. So the more voters you have, the probability that you're in this unique position where the number of people that rank A over B is exactly the same as the number of people that rank B over A, the probability of that happening goes down to 0. Okay, so you might think that a voting method ought to satisfy something like asymptotic resolvability, which says in the limit as the number of voters go to infinity, the proportion of profiles where there's a unique winner before the tie-breaking mechanism, that should go to 1, so that you almost always elect a single winner. Now, split cycle, Getcha, and uncovered set that all satisfy stability for winners, they violate this asymptotic resolvability axiom. So split cycle, the method I really like, has this really cool property. It satisfies stability for winners, but it has this kind of property that you maybe don't like, that even if you have a huge number of voters, split cycle might identify more than one candidate as a winner. So you have to go into a runoff election. Okay. Now, stating asymptotic resolvability as an axiom is kind of annoying because you're talking about the limit as the number of voters goes to infinity. So how do you sort of reason about that as an axiom, at least an axiom that you could feed into a SAT solver? So rather than talking about asymptotic resolvability, we're going to talk about what we call quasi-resoluteness. So quasi-resoluteness says, consider a profile that is uniquely weighted. So what does that mean? Well, if you give me a profile, I can always generate its margin graph. So this is the margin of victory graph. So we have maybe A, B, C, D, say we have 4 candidates right there. Okay, so being uniquely weighted, so maybe D beats B, C beats D, and maybe A beats D. If it's uniquely weighted, the weight of these margins of victory, they all have to be unique. Okay, so it could be something like 2, 4, 6, 8, 10. So the margin of victory for B over C is 10. Every margin of victory is completely unique. Okay, and intuitively, if you have a huge number of voters, that's what you would expect to happen. In fact, you can just sort of see that with probability 1, the type of margin graph you're going to get in those profiles are going to look like that. So our axiom is quasi-resoluteness. So quasi-resoluteness says if you have a profile and the margin graph for that profile is uniquely weighted, then you should elect a single candidate. You should be resolute, at least on those profiles. Now, split cycle doesn't even satisfy quasi-resoluteness. Okay. Our general result is there's a cost to imposing quasi-resoluteness. So you're avoiding tie-breaking lotteries or runoffs. And the cost is this really neat impossibility theorem. There is no anonymous and neutral voting method that satisfies stability for winners and quasi-resoluteness. So those two properties are actually incompatible with each other. I just can't find a voting method that satisfies both of them and satisfies anonymity and neutrality, which are just sort of minimal properties you would impose on any voting method. Okay, so what's the moral? The moral is a small step in the direction of a probabilistic voting method. This is a voting method whose output is actually a probability distribution over the candidates rather than a identifying who does and does not win the election, can help us preserve desirable axiomatic properties. Okay, so we want to prove this theorem right here. So that's what we want to do. We want to prove this theorem. If you think about it, and I want to prove the theorem in a very sort of precise way. I want to know for which number of candidates is it impossible to find a voting method that satisfies stability for winners and quasi-resoluteness. What we actually show, if we just restrict attention to 4 candidates, so you just consider voting methods that work for 4 candidates. I don't care if it doesn't work for 5 candidates, or I just do something special for 4 candidates. Even only for 4 candidates, we can't find a voting method that satisfies stability for winners and quasi-resoluteness. So let's think about what we're showing. So here is the space of all possible voting methods. So a point in this space is going to be a voting method. So this is a function that maps profiles for 4 candidates. And let's fix a certain number of voters. It doesn't really matter how many voters we have, but some finite number of voters. But it maps profiles to some winning set, which we'll call Y. So it's a map from profiles, this is like an election scenario, to some set of winners. And then we have another point, this is another voting method. So do a little bit of finite combinatorics. If you have 4 candidates, that means you have 24 possible linear orderings. So we're restricting attention to linear orderings. Then you consider all possible sequences of those 24 rankings where you have maybe 10 voters or 15 voters. And then you look at all possible functions on that map those, any sequence to any subset of candidates. That is a huge number. That is just astronomical, okay? So this is a huge space. Nonetheless, we can sort of think about it and we can say, well, look, we're in this space, and what I want to do is I want to restrict attention to the anonymous and neutral voting methods. So I want to restrict attention just to this space right here, the anonymous and neutral voting methods. And now what we're asking is, if we restrict attention to the voting methods that satisfy stability for winners and quasi-resoluteness, is there a voting method in this intersection or not? So is this intersection empty or not? That's what our impossibility theorem is going to say. This is what it looks like. Okay, this is what our impossibility theorem proves. Okay. Now, the problem with trying to apply a SAT solver is, even if I restrict attention to finitely many voters and finitely many candidates, this is just an astronomical number of voting methods. So how are you going to encode this in as essentially a propositional formula? So one thing we're going to do is we're going to restrict attention to a certain class of voting methods that's going to make it very easy to encode it as a SAT in a SAT solving, like as a propositional formula, and to throw it as at a SAT solver. The voting methods we're going to restrict attention to are called pairwise voting methods. Okay, so let me explain what a pairwise voting method is, and to do that I need to be just a little bit more precise with my notation. So we're thinking of anonymous profiles. So, well, first of all, given any set of candidates, let L of X be the set of all linear orders over the candidates. So we're not allowing voters to submit ties. We're ruling out that case right here. Then an anonymous profile is just a function that maps any linear order to the number of candidates in that profile, the number of voters in that profile that have that ranking, right? So if P of, let's say, A, B, C is equal to 7, that means 7 people have the ranking A above B above C, and so Okay. Now the margin of victory is just going to be the margin for A over B is the number of people that rank A above B minus the number of people that rank B above A. And then an anonymous voting method is just somebody that takes one of these anonymous profiles and identifies some subset of the set of candidates in that profile. So X of P here, this is the set of candidates in the that show up in the profile P. Okay. Separate than that, we can define a what in the literature is called a weighted weak tournament. And that's just this weighted graph that we've been talking about. So 1, 5. This is an example of what's known as a weighted tournament. I call it a weak tournament because I allow some edges to be 0 in general. So it doesn't have to be a complete graph. Okay, and that's what don't worry about this definition right here. For technical reasons, we have to think of a graph as a matrix. But there are two ways to represent the same thing. So just think of it as this weighted directed graph that we've been talking about. Okay. Now, given a profile P, we can always define the margin graph of P. That's going to be the weighted directed graph whose vertices are the candidates that show up in P. And there's an edge from A to B weighted by the margin of victory for A over B. And you only draw edges if the margin of victory is positive. Okay. Then we say that a voting method is pairwise if for any two profiles, if they have the same margin graph, then you have to identify the same set of winners. So roughly, when you identify the set of winners, you're only allowed to look at the margin graph. You're not allowed to look at any information except for the margin graph when you identify the set of winners. Okay. So we're going to restrict attention to pairwise voting methods. Now, that's still a pretty big set of functions, if you think about it, even if you have like 5 candidates or 4 candidates or whatnot, that could still be quite a big set. Okay. What we're going to do is, rather than thinking about pairwise methods, we're just going to act directly on a tournament solution. So given a tournament, so one of those weighted directed graphs, then my function is going to identify a set of winners for that particular tournament. Okay, so rather than thinking of, obviously there's a close relationship between pairwise voting methods and what are called tournament solutions. Okay, so here's what we're going to prove. There's no neutral weighted tournament solution satisfying quasi-resoluteness and stability for winners for this set of tournaments. We're going to restrict attention to weighted tournaments that have at most 4 candidates, and all of the positive weights come from 2, 4, 6, 8, 10, or 12. So this makes it nice and finite, so I can encode this as a propositional formula. Otherwise, if the weights were allowed to be anything, we would have a domain that has infinitely many different possibilities. Okay. All right, so this is what we proved. This is what I'm going to use a SAT solver to prove this fact right here. Okay. Now, there's a little bit of a problem here. So suppose I prove this, right? And I'm happy, I pat myself on the back. I'm really happy I use a SAT solver. It's really cool. I encode this as a propositional formula, and I actually prove this. And now I go to my colleagues in the social that do social choice theory, and I say, hey, look, I proved my impossibility theorem. They can rightly come back to me and say, well, no, you impose this extra axiom that you restrict attention to pairwise methods. Why should I restrict attention to pairwise methods? And in fact, this is what could, like, it's logically possible that something like this could be happening, right? That on the space of pairwise methods, stability for winners and quasi-resoluteness, they don't overlap. But outside of a pairwise method, in fact, there might be a voting method in this little region right here that satisfies anonymity, neutrality, stability for winners, and quasi-resoluteness. All you showed with your SAT method is that there's no pairwise method that satisfies that. Okay, so an important part of what we try to do in our paper is give a general framework for arguing that once we've determined that this is the case, then we can just appeal to one of our theorems to prove that there can't be a voting method up here. Okay, so that's another sort of cool aspect of our paper. So I'll explain that in just a second. Okay, all right, great. So yeah, I'm doing pretty good on time here. So this is good. So let me first talk about the SAT encoding. So what I want to talk about is this result right here. When we restrict attention not to pairwise methods, but tournament solutions. And I want to prove that there is no tournament solution satisfying stability for winners and quasi-resoluteness. And for this, we're basically just going to use ideas that Felix Brandt and Christian Geist have already employed to prove impossibility results using SAT solvers in social choice theory. And in particular, we draw very heavily on this paper and their encoding. Okay, they don't really think about variable candidate axioms like stability for winners, so we have to extend the result to that setting, but that's okay. Okay, so let me explain the key idea of how we encode the problem in SAT. So for any tournament T, so remember, what is T? T is going to be something that looks like this. So it's going to be a directed graph. And let's see, so something maybe like that, and it's going to be weighted. So there's going to be weights drawn from 4, 8, and 12, something like that. It's going to be a weighted directed graph. If you give me a weighted directed graph and then any subset of the nodes that show up in that weighted directed graph, we're going to have an atomic proposition, A sub ty, that means y is the winning set for t. Okay, this is going to be the key to our encoding. Now, the first thing we're going to do is we're going to restrict attention to weighted weak tournaments with positive weights from 2, 4, 6, 8, 10 to 12. Okay. We're going to restrict attention to weighted tournaments. So we're going to throw out the possibility of having no edge between nodes. So that reduces the number of directed graphs that we need to generate, which is reducing the number of atomic propositions that we'll actually have. And then there's another sort of real technical thing that I don't want to get into for the purposes of the talk. But it's just not the case that any possible subset of X of T, of the set of nodes in a tournament T, can be identified as a winning set for that tournament. So in particular, if you give me two tournaments that are isomorphic, then obviously their winning sets have to be equivalent up to that particular isomorphism. And furthermore, we can't assign a winning set that would force us to violate neutrality. Okay. So like I said, I don't want to, if we, in the question period, you can press me on this, on how I actually do this, but following ideas that of Brandt and Geist, what we're going to do is for every tournament T, this is like a pre-encoding step, we can identify, here, for any tournament T, we can identify this O of T, and this is the set of possible winning sets for T. Okay, and these would be the ones that you could possibly assign to T, winning sets you could assign to T, and you won't be forced to violate neutrality or anything like that. Okay, and one last thing we're going to do is rather than working with all possible tournaments, we're just going to consider the space of all possible, uniquely weighted tournaments where you draw weights from this set right here. And then then you like consider the isomorphism classes of all of those tournaments, and we're just going to pick a canonical representation from every possible isomorphism class. Okay, so that makes it a more efficient encoding. Now,
can I ask?
Sure, yeah.
Yeah. So, in any special reason why you choose weights only from that class?
why is it these even numbers and not like 1, 3, 5, 7, 9 or something like that? Or so the one thing it can't be is the parity has to be the same. And I'll explain why that's but the parity has to be the same because the number of voters is either even or odd. But if you think about it, when you generate a margin graph, the parity of the weights are always going to be the same. There's no reason why we chose even as opposed to odd. It makes it convenient for something we're about to do later on. But outside of that, no,
but like
there's no
something like replace 12 by, let's say, any random number, 100. And will that change?
Yeah, you could replace it with, that would be fine. That would be fine, actually. Yeah, that would be fine. In fact, if you think about what's going on with the SAT encoding, it's really not going to matter what those numbers are at all. The numbers don't play a deep role because, well, yeah, they just don't play a deep role in the SAT encoding. Yeah, that's a good question. Yeah. Okay, okay, here we are. Okay, so here's the first function or the first formula. It's just that our encoding gives a function. So let's look at this. So this says, for every tournament we're considering, for every possible winning set, somebody is a winner. There exists somebody that's a winner. And it can't be the case that TC is associated with Y and TC is associated with Z, where Y and Z are different winning set. So every tournament T is associated with exactly one winning set. So this is just a description of the function. Everything here is finite. So this is a conjunctive, a propositional formula written in conjunctive normal form. Okay. Quasi-resoluteness is super easy because we just do that at the level, we just restrict attention to tournaments that are uniquely weighted. So our propositional formulas don't even mention tournaments that are not uniquely weighted. So quasi-resoluteness is just resoluteness. It says you can never assign a winning set that has more than one element in it. Okay. The complicated one is stability for winners. So the stability for winners formula is this one right here. And the idea is actually quite simple. It says for every possible tournament, is there any restriction to the clause size? No, there's not. In general, no, there's not a restriction to the size of the clauses. I mean, there will, as a matter of fact, I can tell you how many clauses there are, but no, in general, there isn't. So let stability for winners be this formula right here. And basically, here's the idea. So T prime of C, that's going to be the smaller tournament right here. T of C, that's going to be this bigger tournament right here. And T prime of C can be embedded in that by some type of embedding. Like there's a you know, like a graph, I wouldn't say isomorphism, but it's an embedding in the model theoretic sense of this graph into this one right here, right? So what you say is for every possible winning set for T prime C, if Y is the winner in the smaller set, then the winning set for the bigger tournament has to include at least a couple candidates. Namely, look at these candidates, A2 and A1 right here. A2 and A1, they get mapped to E of A2 and E of A3. And notice, A1 gets mapped to E of A1 and A2 gets mapped to E of A2. Notice both of them are majority preferred to this new candidate B, right? So if Y is a winner, then the winner in the bigger set has to include, so, you know, if these two things were in Y, if these two candidates were in Y, then Z has to include, well, E of those two things. You know, you apply the embedding to each of those two candidates. So this formula right here really just is stating stability for winners. Okay. All right. So this is literally what we prove with the SAT solver. We restrict attention to those atomic propositional formulas. And then we encode this as a SAT solver, and we throw this to the SAT solver, and the SAT solver responds, this is unsatisfiable. I can't satisfy find a function, quasi-resoluteness, and stability for winners. I just can't find one. Okay, so good. We're happy. We now are in this situation for weighted tournament solutions. There can be no tournament solution satisfying stability for winners and quasi-resoluteness. Okay. All right. Now, notice I pulled a fast one on you. I was talking about pairwise voting methods, and then I said, oh, well, let's just restrict attention to weighted tournament solutions, because that's easier for the encoding. So what we want to do is, what we really have is we have the weighted tournament solutions, and we want to know, can we find a voting method here in this region right here? Right? So yes or no, are we able to do that? Okay. Now let me, okay, good. Yeah, so I have time here. So what I want to do, so we think of this as leveraging the impossibility result over the class of weighted tournament solutions. How do you extend that to a result over the space of all possible profiles? Now, of course, one thing I could do is say, well, Eric, it's fine. All you have to do is figure out a way of encoding all possible profiles rather than tournaments, right? Rather than restricting to weighted directed graphs, why don't you encode all possible profiles? And that's certainly a possibility. I'm not saying that that's impossible. It does raise some computational problems. I don't think it raises problems necessarily for the SAT solvers. It raises problems for how do you generate the clauses you need to feed into the SAT solver, because you need to iterate over the space of all possible profiles. And how do you do that when that space is too big? Okay, all right. So that's what I want to talk about now. Now we're going to draw on, there's a really cool result it's called the McGarvey-DeBord theorem. And what it says is, if you give me any weak tournament, so every weak tournament, so give me any weak tournament, so any weighted directed graph, I know that that is always the, every weighted weak tournament in which all the weights have the same parity is always the margin graph of some profile. I can generate a profile that would have generated that weighted weak tournament as long as the weights have the same parity, okay? And to illustrate what's going on, suppose that I give you this weighted directed graph, right? The DeBord construction says I can find a profile such that this profile, the margin graph of this profile is exactly equal to this weighted directed graph. And how does it work? Well, it's a very clever idea. Here, look, the margin of victory for A over B is 4. So I'm going to divide that into 2. So these two people have A over B, and these two people have A over B. Right? But now I need to know, I don't, when I add those 4 voters, I want the margin of victory for A versus C and B versus C to be 0. I want them to be tied when it comes to A versus C and B versus C. So I just divide that in 2. Half of them put C at the bottom and the other half put C at the top. And of course, if we had more than one candidate, that would work. We would just do C over D, and that would be D over C. You would just take linear orders and make them reverses of each other. Okay, so this works in general more than 3 candidates. Okay, and you would do that for 8 and 12. Now you can start to see why I like even rather than odd. you can deal with the odd numbers, but it requires a little bit more work, and I want to set that aside. Okay, all right. So here's a really cool, especially for logicians, people in this group, given the previous talk, we love commuting diagrams. So you can, given a profile P, suppose you're given a tournament solution. You can take that profile P, generate its margin graph, apply the tournament solution to it, and then pull it back to get a voting method on profiles. Or given a tournament solution, you can apply the Debord rule. If you have a voting method who identifies the set of winners, you can pull that back to give you a tournament solution. Okay, so maybe we can leverage Debord to kind of, generalize our result to all possible profiles. Well, we can, as long as we restrict attention to pairwise voting methods. Okay, now it should seem pretty obvious that one can actually do that, but there's a problem going beyond pairwise methods. And that problem is that the Debord construction does not commute with transposition and restriction. So let me illustrate what's going on here. So in order to do this, suppose that I have a voting method that I know is neutral, right? Now, what my result says is that there's no tournament solution having such and such property, right? So, what I want to be able to do is take my voting method and define a tournament solution from that voting method. Okay, well, I can do that. I take G of T, I first apply the Debord construction representation to T, and then I apply my voting method to it. But I need to prove that this method is in fact neutral. Okay, so let's think about what you have to do. Starting from a tournament T, I identify the winner in the following way. I apply Debord, I apply my voting method, and then I pull that back to get the set of winners. Now suppose I take a tournament and I transpose A and B. I swap A and B. Okay. By neutrality, the winning set has to be swapped as well. So if A was a winner and then I swap A and B in everybody's rankings, then B has to become a winner. That's what the neutrality property says. Okay, well, fine. I swap A versus B. I apply Debord to it, apply the function to it, and then pull back. So I have to know, is it the case that this set, this is a transposition of that set right there? Okay. Well, what that is asking is, if I take a tournament T and I find the Debord profile representing that tournament, and then suppose I transpose A and B in that profile, do I get the same thing as if I would start with that tournament, transpose A and B, and then apply the Debord construction to it? Sadly, the answer is no. You don't get that. When you apply Debord, you get this profile right here. Here I've transposed A and B. So let's just look at that. Here's A, here's B, here's B, here's A. So I just flipped A versus B. So if A was a winner over here, then B would have to be a winner over there. Otherwise, you're treating the candidates unfairly. If I find Debord, what you end up is this profile right here. But if I were to take this profile and just swap in everybody's rankings A and B, I get not the same profile, because in this little region right here, they have different rankings. So these profiles are technically different. I mean, not technically, they are literally different. They're different profiles. Okay. So what we have is not that this profile is the this profile is the transpose of that profile, but rather what we do know is that their margin graphs are the same. So if you go back over to here, I do know that these two margin graphs have to be the same, but the profiles are different. Okay. So that's why I have to appeal to pairwise, because all I know is that these two margin graphs are the same. And if the margin graphs are the same, then I can state the appropriate relationship between those. The same thing happens for trying to satisfy stability for winners. If F satisfies stability for winners, and you go down to, and you generate this tournament solution, does it satisfy stability for winners? Okay. So what do you have to do? Well, you have a tournament. You restrict it by throwing out candidate B. So you throw out candidate B. Now, the relationship between these winning sets is a little bit more complex. It says if A was a winner in this smaller set and the margin of victory for A over B is positive, then A has to be a winner in that bigger set. But it doesn't matter. There just has to be a relationship between those two sets. So again, the problem is when you apply to board, you get something, and then you could restrict by throwing out candidate B. Do you get the same thing as if you were to start with a weighted tournament, restrict, and then apply to board? And again, this doesn't work. And this is even more obvious that it's probably not going to work. If I applied to board here, I have this candidate D floating around. So when I remove, say, candidate D, then I'm going to actually have lots of extra copies of some rankings, A over B over C, and so on. I'll have lots of extra copies floating around that you wouldn't actually get if you just applied to board directly. Now, again, these have the same margin graph. So for pairwise methods, it doesn't matter. But for non-pairwise methods, we're not going to be able to show that my tournament solution satisfies stability for winners. Right? So again, we need this sort of crucial step. So to extend this result, we have to come up with a different way of realizing profiles. Realizing, given a weighted directed graph, we have to come up with a different way of finding profiles that behaves properly. It needs to commute with restriction, and it needs to commute with transposition. Okay, so the idea, it's a little bit more complicated to figure out how to deal with restriction. But let me just explain to you the key idea of our representation. So we're going to start with this tournament right here. A is preferred to B by 4, B is majority preferred to C by 8, and C over A by 12, and so on. Here's the first thing we're going to do. We're going to consider all possible linear orderings over those 3 candidates. So there's 3 candidates, so there's 6 possible linear orderings. So we're going to consider a profile with all of those. So we're going to have a lot of voters. I'm going to, for each group, I'm going to have 6 voters that have each of those possible linear orderings. Okay. And now here's what I'm going to do. I see that A over B, A is majority preferred to B by 4. So I'm going to go here and I'm going to find the group that has B over A at the top. And I'm going to flip as many of those as I need in order to create a majority preference of A over B. So what do I have to do? Well, I take this group and I flip 2 people from B over A to A over B. And if that's all I did, I would end up adding a margin of victory of 4. Every person you flip reduces a loss by 1 and adds a win by 1. So you get a margin of victory of 2. Flipping every single person gives you a margin of victory of 2. It raises it by 2. So I flip these 2 people from B over A to A over B, and I don't make any other changes. The margin of victory for A over B is going to be 4. Now you can see why I need at least 6, because the biggest margin there was 12. So, the minimum thing I would have to do is flip everybody in this group from A over C to C over A. Okay. So this is great, but how on earth are we going to get this to commute with restriction? So the idea that we have is actually when you apply this representation, you have to tell me, am I thinking of this? Is this eventually going to be embedded in some profile with, say, 4 candidates, with a set Y that has those 4 candidates in it? Or is it going to have D and E or whatever? I need to know who are the people that you're eventually going to add to this profile. So what we do is we actually generate a representation of this graph right here, given a set Y, given sort of the biggest set of candidates. Okay, I'm not going to go through this just in the interest of time, but this is really it's the same basic idea, except you start with 4 candidates rather than these. And then when we want to realize this, we just throw out that 4th candidate D. We just kind of forget about him. And that gives me enough extra voters with enough extra rankings that it will commute with representation. With restriction. So our method does commute with transposition. It does also commute here. You can see that this commutes with restriction as well. So it commutes with both restriction and transposition. Okay. All right. So here's the key idea, and I'll finish up in the next 2 minutes here, 3 minutes here. Okay. So here's the key idea. Given any voting method, so suppose we have an arbitrary voting method. This is just some random voting method. I'm going to define a pairwise projection of that voting method. So basically what I'm going to do, giving that voting method, I'm going to define a pairwise voting method from that original voting method in such a way that if that original voting method satisfies stability for winners, then my new method will, then this pairwise method will satisfy stability for winners, right? So that's what I have to do. I start with this profile P right here, and I want to define, now it's a little bit complex because I need to give this finite set Y because I wanted to, to satisfy stability for winners. But you'll see where Y comes from in just a second, okay? And we also need to give it a fixed number M. But here's the idea. We start with this profile P. We look at its margin graph. Now, for technical reasons, we can't just look at that margin graph. We actually have to multiply all the margins by this number right here. 2 times the number of candidates minus 2 factorial. That ensures that it'll commute with restrictions and stuff like that. Right, so we start with this profile P, generate its margin graph. Now we go to our cool method of representing margin graphs. So now we have a new profile right here. Okay. Now, so this is our profile. Let's just assume that it's in the domain of this function f. So we work with universal domain. We apply our function on that profile, and then we just say, hey, okay, that's who the winner is in the original profile. Okay. And now we have this really cool result. If you have a voting method f, and then for any set y and any number m, this is going to be pairwise. And if this method f was neutral, then this method f would also be neutral. And furthermore, if this method satisfies stability for winners or quasi-resoluteness, or actually we characterized the logical form of the axioms it has to satisfy, then this voting method, FPYM, would also satisfy that axiom. Okay. So to summarize in a picture, here's what's going on. Our proof is actually quite simple. Suppose that there was a voting method F that satisfies stability for winners, quasi-resoluteness, anonymity, and neutrality. So there is a voting method F that lives in that little region. Well, we can find a pairwise method, right? So we can use our projection to find this pairwise method. And we know that this pairwise method must satisfy stability for winners, quasi-resoluteness, will be anonymous, we built that in, and will be neutral. But now we go to our SAT solver, and the SAT solver said no such method can possibly exist. So this space has to be empty, right? So the picture indeed looks like this. This is indeed what it looks like. Okay. All right. So, I'll skip that. You can ask me in question period. So although SAT solver in the literature is limited to pairwise methods or, which is kind of a weaker class called C1 methods. So in the existing literature, it's typically limited to that. SAT solving plus just a little bit of additional theory, this new representation that we actually come up with, allows us to obtain these general impossibility theorems. So in particular, we prove that there's no voting method satisfying anonymity, neutrality, stability for winner, and quasi-resoluteness for up to 4 candidates. But there is one up to 3 candidates that we proved the old-fashioned way, just using finding a method that satisfies those properties. In the paper, we also look at another impossibility theorem. We look at a probabilistic version of stability for winners, which basically there's no method that satisfies a natural probabilistic generalization of stability for winners. Here, interestingly, you need a minimum of 6 candidates to find the impossibility theorem. You can find one for 5 candidates, which is kind of neat. Now, a natural question for further research concerns optimizing the number of voters. We said, well, look, we want to commute with restriction. The trick to our representation is to have lots and lots and lots of voters, right? You have 1 voter for every possible linear ordering. So we're sort of not caring about optimizing the number of voters. I don't think it's impossible to possibly optimize the number of voters using our ideas, but certainly what we currently have presented, we can't just sort of say, oh, restrict attention to only 5 voters or something like that. That just won't, that our projection won't work in that case. We do think that this should be applicable to other impossibility theorems. So if you do have an impossibility theorem involving just tournament solutions, you might be able to generalize it to an impossibility theorem involving all possible voting methods. So I think I am out of time, so I will just go ahead and stop here and just say thank you all very much. I hope you enjoyed it. That's all I wanted to say. So thanks a lot.
Such an excellent talk. Now I just
Thank you.
want to ask our audience if they do have some question.
Sure.
Is there any question?
Yeah.
Yeah, Amit. Yeah.
So these projection methods, do you think that given any set of properties, you can generate a projection to?
Okay, so that's a really good question. So in our paper, we restrict attention to universal properties. I mean, these really have the form for all profiles P. Or maybe for all profile P, for all profile P prime, if P and P prime are related in a particular way, then the winning sets have to be related in a particular way. And that generally works. So like when I stated this theorem right here, oh, well, I already lost it. But when I stated this theorem right here, this AX in the paper is actually, we just call it a universal axiom. Now, it becomes even more interesting with an axiom, this probabilistic stability for winners axiom. Yeah, so I don't want to get into the weeds too much, but here we restrict attention not just to weighted graphs, but just unweighted graphs. So we're working with C1 methods. This axiom is not a C1 axiom, so the axiom has to be invariant in sort of applying, finding the majority graph. But we call it quasi C1, and we actually show that it actually, like a slight extension, would actually work for that class of methods. So if you said, Eric, what exactly is like the logical form that you need in order to apply this projection. I don't actually know, because you know we have a little bit of wiggle room in which we can say, oh, well, don't consider that axiom, consider a close variant of that axiom, and then any voting method that satisfies that original axiom will satisfy this close variant, and that one, then you can apply our projection to it. So you might need to project the axioms in addition to project the voting method. But it's a good question. It's a really good question. Yeah.
So it's like you are choosing something from the equivalence class. You are choosing a representative, basically.
That's right. That's right.
Satisfies certain.
Yeah. No, that's yeah.
Thanks a lot.
Yeah.
Is there any other questions? If not, Eric, I wanted a kind of clarification, I should say. Maybe I had some. Sure. So actually, I wanted to understand intuitively, what does it reflects that having different different profile having same margin graph. So what does it actually represent intuitively? That I wanted to know.
Okay, that's a good question. Okay, well, so that it's just a fact that you could have different profiles that give you different margin graphs, right? I mean, just consider kind of a trivial thing where you have a margin graph with A over B, and you have the margin of victory is, let's say, 7, okay? Now, think of the profiles that might generate that. There might be one profile that has exactly 7 voters, and all of them rank A over B. You might have another one where you have thousands of voters, and the margin of victory for A over B is just 7, right? Those are wildly different voting scenarios. You might say, oh my God, that's like wildly different. If your voting method is pairwise, then you have to ignore you have to treat those equivalently, right? Because all you're allowed to look at is that information. Now, there's a way to kind of deal with there is a way to kind of deal with that sort of extreme case. But you might argue that, you know, all these different profiles, you know, they all have, you know, if they all give rise to the same margin graph, why now? So here, you know, do we want to think of it like as an axiom of social choice theory that all those profiles ought to be treated the same? Like, as a matter of fact, there's voting methods that only pay attention to the margin graphs. Like my voting method that Wes and I came up with, split cycle, that only pays attention to the margin graph. It just like ignores those things. Other voting methods, minimax, beat path, and so on, that's like built into the algorithm. You only pay attention to the margin graph and you ignore everything else. But you know, it's not so nice for like an impossibility theorem. If you use that impossibility theorem to say, my voting method is really good, well, here's the first thing you have to do. You have to restrict attention to pairwise based methods. Why? Well, that's because it's what I do, and you have to do that. So you don't want it to be kind of like an axiom that you add. Otherwise, because you would have to give sort of independent justification to answer your question right there. And so that, you might argue, that's why we did so much work at the end, why we weren't just satisfied with ending up with showing there's no pairwise method satisfying that, because then you kind of shrug your shoulders and say, yeah, okay, well, that's nice, but what if I don't like pairwise methods? What if I like other methods that are not pairwise because I don't actually want to do that? So it's a really, really good question. That's how I would think about it. Yeah.
Thanks a lot for such nice.
Sure.
Yeah, just one more thing to say. So Sujata apologized to you that she had to leave.
Oh, okay.
Yeah, no problem. I think at the beginning. Thanks a lot for such a nice talk. Seriously.
Eric, I have one more question. Can I?
Yeah, sure.
Oh yeah, of course.
So, is there any characterization of ultra products using impossibility results? Like the reverse question.
Well, okay, so there's okay, yeah, I see. There's there is there's a paper. Now I'm forgetting who the authors actually are, which gives sort of a model theoretic analysis of Arrow's theorem, where indeed, because you can think of an alter product as being a bunch of models or a bunch of voters that are voting on whether or not A is preferred to B, and stuff like that.
That's Abramsky, right?
Well, yeah. So I'm thinking of something a little bit earlier, but Abramsky has he has this nice paper, Arrow's theorem by Arrow theory or something like that. What he does in there is slightly different. I'm thinking of something a little bit earlier, where they sort of just noted an analog between like finding an alpha product and like think about how do you teach that when you teach it to students. You like imagine each of these models, and the models are all voting on whether or not the AD is in some relation or something like that, and we just side with like the majority or the biggest group or whatever, and that's given by the alter filter. So this is all related to doing voting when you have infinite populations, when you have infinitely many voters, and there are some papers there. Right now I'm just blanking on who the authors are. Usually I remember these things, but right now I'm just kind of blanking on that paper right there. So if you send me an email, I can definitely find, because there's like Fishburne has a result, but there's a whole sort of series. There's a more recent paper. I think Hertzberg, Frederick Hertzberg is one of the people that is a recent author of this. Anyway, yeah. So it's a good thought. I see why you're asking this question. Yeah, it's a very good thought. Yeah. It might seem out of left field, but actually, it's exactly right. I mean, it's exactly the right thing to think about. Yeah, that's a good question.
Yeah. Thanks.
Other questions?
Okay. Thanks a lot. And if there is no.
All right. Thank you so much.
Yeah, thanks a lot that you gave a talk early morning. That's good for us.
No problem. This is great. This is a lot of fun.